So based on what we have covered so far, or um, based on how you design your study, first we come up with a hypothesis, then we design the experiment, then we collect the data, and then we correct, like we do a quality check, right? And after quality check, what we do is on a box or on a subject-wise basis, we make some measurements, right? So far, based on what we have studied, like one measure that we have used is functional connectivity. So it could be correlation, it could be GLM, and once we collect that across a large number of subjects, then what to do, right? And so we will cover about that. So as I have said, the simplest of test is the t-test, because you can use t-test to compare with a null distribution. Like you can collect 10 subjects, healthy subject, and measure their, let's say, sensory motor connectivity, and then ask this, that compared to null hypothesis, which is that there should not be any, how does it compare, right? So if you are doing sensory motor connectivity, then you should be able to identify a group level difference of the sensory motor cortex, right? Similarly, I mean, for task activation, you could also do where, if you were being shown like a visual stimulus and you scan like 20 subjects, then only the visual cortex should be activated, and by doing a t-test, it should identify the visual cortex. But if instead of that, right, instead of correlation value, you had other measures like GLM, you can also use those measures to do group level analysis. So most of you know what t-test is. Does anyone know what ANOVA is? Right, but what does it tell you? More than two groups. But you can also do pairwise, right? If you have three groups A, B, C, you could do A, B. Yeah, so why would you then use ANOVA? Two. Good. So that is another very common method which is used for data set, which is a little more complex, right? So I showed you this. So let's say this is one group. You have like task 1, task A, and then this is repeated across many different subjects. Then the challenge really is, can we somehow use like a modeling to reduce these effects? Wow, Sanchita, that's power. Even I make jokes, there is noise. Okay. All right. So when you collect a series of data, then um, no problem. Okay. All right. So as we collect data from many subjects, our goal is that we should somehow reduce um, these measures into a more conceptual framework or define it in quantitatively, right? To describe about how much variation is there across the different subject or within the subject across different trial. Right? And by doing that, we can reduce the computational hurdle. Um, of course, every time we do this, we have to make assumptions regarding the nature of the data, right? Um, if our group is between 18 and 80, should we consider it as one group or should we consider it as two groups, young and old, right? But again, with these, like where you set the threshold of defining someone young and where it's like a binary cutoff. So all those things can affect our analysis method, but as long as we define how we process our data, then it is okay, right? This is, again, another way in which we can uh, think of the data that we get. So this is brain, this is like different resting state networks, and within each network, there may be different number of regions, right? And then again, here, the assumption we are making is that if in region one there are, you know, V number of voxels, then one assumptions we are making is that these are all neuronal, right? Which again may or may not be true, right? But for approximation, we can approximate. Um, and as the model becomes more complex, we can think about, in this case, can we include other measures which would make it um, based on the question we are asking. Um, so this is why individual analysis should be followed by group analysis, or some people are now saying population analysis, as like different group may have like hundreds of subjects, and that is typically much more than what was done. So I think they are using population analysis. So uh, with integrative modeling, the ideal scenario would be that if there was one model that could incorporate all the hierarchical level, and that there would be very little information loss, right? Again, this would be very, very difficult to do because it's hard to think of a design which could be applied universally, right? Even for finger tapping, again, as I have said, for healthy subject and even for little kids, you can ask them to tap their fingers. But even if um, so you cannot do infant or clinical population, but let's say you wanted to introduce even a little bit of difficulty and ask them to tap like in a certain sequence, some people may not be able to do, right? So then you're not able to maintain the level of difficulty for all the subjects. And so therefore, like having one simple model is very, very difficult to have. So therefore, people have used like two-stage or multi-stage analysis. So at the individual level, you can do time series regression for GLM. And again, like this is the command which is used, like because some of you said you know AFNI. So this is the command for AFNI to do GLM kind of analysis. Right? So again, on the individual level, you can find the beta weights, right? Like for GLM, you can write y equal to beta x plus epsilon. And so you're getting like it's called the beta coefficient. Like in correlation analysis, it is called correlation coefficient. But in this case, you can account for the underlying hemodynamics and then do GLM kind of analysis. And then once you have done that, then you can look at the group level for that response variable, right? And these individual level effect estimates, which is the beta value, and their uncertainty information predictors like experimental factors, covariate sex, age, and so on. Again, for this kind of study, we can have like two types of samples. It could be trials and participants, right? And then also two kinds of generalization, like task condition, individual to population. Also, in this case, you can have like prior assumption, like across individual or across variability. And like cross trial variability, people try to account for it as much as they can, right? It's like, let's say someone was scanned on Monday morning versus Tuesday or Wednesday morning. Can you expect any kind of difference, systematic differences? Like, do you think there would be any difference if the students were asked to come and be scanned on Monday morning versus Wednesday morning, for example? Like subtle differences. What could be the reason? Okay. Okay. But I think okay, so there should not be, but there should not be. Maybe what Rahul was mentioning about sleep, can anyone elaborate? About sleep, Monday versus Wednesday. Very good. And on Tuesday night, suppose the person is doing programming up to late night for the assignment. Okay. All right. Yes. Yes, certainly. Yes. So those things can affect also, if someone had an exam on Monday versus there was no exam on Wednesday, like even like little things can technically affect, um, but we ge- but it's very difficult to control for that, right? Because it's like you cannot really control how much, um, like the amount of sleep someone is getting every night, and there will be variation based on the weekend or weekday. So while it may affect, those effects generally, unless sleep is the focus of your study, um, those cannot be that easily controlled, right? But nonetheless, they are factors which could be used. Like, so people have done like the effect of sleep, effect of breakfast, like whether you had any food, if someone drinks coffee um, every morning, right? If you if they were a participant in your subject, would you allow them to drink coffee and or not, right? And if someone else, um, you know, is smoking, right? So what should you do? So sometimes, depending on the focus of the study, you like either assume that these are small factors and you like um, not worry. But if these are some of the factors, then you have to take very good or I should say, as much information as you can, and then use it as regressors in your GLN analysis. So again, among factors, there is within versus between individual factors, right? Between individual is like healthy subject versus autistic, or male versus females. These would be the factors. Again, if you were to do, let's say, healthy subject versus autism, you can use t-test, right? But if you want to study um, like sex differences in autism and healthy control, then what analysis would you use? ANOVA, right? Because there are multiple factors. Um, so for so these are like discrete factors. For quantitative, it is like could be within versus between individual, and between individual would be age, like cross-sectional age, like brain volume, right? And within individual would be age, longitudinal, and rating across condition, right? You can have like for people who are at risk of Alzheimer's, um, some people are scanned maybe once every year or so, right? So in those cases, this would be within individual study where you are scanning someone once a year or once every 6 months and looking at their progression or changes in connectivity or other brain measures. And then between individual would be, let's say, like two of you were scanned, then I would have to, like, one should also take um, age as a factor, but more importantly, maybe brain volume or height or weight. Those could be other factors also, right? As to maybe there is a correlation between brain size. So that would be ways to do. And covariates are all explanatory variables, as well as variables of no interest, right? So like the motion parameters and so on, as well as, um, you know, um, let's say IQ, or how well you are doing in a test, like the cognitive test, they all are covariate. Like depending on what you're studying, um, it would be either of interest or of no interest. Um, as I had mentioned before, there is um, a fixed effect and random effects, right? And fixed effect in this case implies like constant, um, like population level, which is condition group, effects of interest, right? While random is varying, low levels participant trials, exchangeable and generalizable. In resting state, um, for many of these analysis, when we say fixed effect, it is the connectivity profile, right? The functional connectivity profile, which is meant. And then, as I said, for model structure, like t-test is used, or ANOVA is used, as well as there are other hierarchical models like Bayesian and other models which are used now. Right? And then as we use different methods, there is always this issue about um, accuracy versus precision, right? Like type 1, type 2 error. So again, so for group analysis, the t-test, and like MEMA stands for mixed effect analysis, like GLM, ANOVA, and COVA. These are the method, and MVM is multivariate modeling method which is used. Also, for the group analysis approaches, the other thing we use is like assumed HDR, hemodynamic response function, versus the estimated hemodynamic response function. So both can be used depending on the application, right? So if we were to study one group, uh, one young healthy group, then maybe we can assume that the hemodynamic response function across different subjects are similar, right? However, if you were to study young versus old, or healthy versus disease subject, one would have to estimate the hemodynamic response function, because you cannot make an assumption that they would be similar, right? I mean, you can assume, but then the result that you get may not be correct. And then there are also issues with covariates, how many to use, which one should be of interest, which one should not be interest. And then there are, for other kind of analysis, like movie watching, um, and to compare different measures, interclass correlation coefficient is used. So interclass correlation coefficient is a method where you can compare when the measures are different, right? So if you have, you you study the subjects, once you, let's say, are estimating one measures of connectivity, the second time you're using a different measure of connectivity, to see how reliable connectivity is, you can use interclass correlation coefficient. For intersubject correlation coefficient, um, this is mostly used for movie watching, right? So in movie watching, what is done is that um, if everyone watches the same movie, while there will be differences between our responses, but it will be very similar, right? So what can be done is that remember how in uh, correlation analysis, you take one time series and correlate with every voxel in the brain and get a map, right? So in intersubject correlation, what is done is, let's say 25 of you watch the same movie clip, right? So from one region, right, let's say Rahul's time series obtained, then it will be compared with the rest 24, right? So you will get, then Shreyans's time series will be taken from region 1 and correlated with the rest 24. So then what you will get is a 25 by 25 correlation matrix, and that will tell you how does each one's brain response compares to the other one, right? So if someone dozed off, then you can very easily find out, right? But also you can use this to show differences between, let's say, whether, we could find out, whether not only does he like animal, but maybe they like Three Idiots also, right? So that is how you can do comparison, find common features as well as differences. And because you would have all these measures, you can see whether there is a difference between the two groups. Okay. All right. So again, we use group analysis because it helps us give information about reproducibility and generalization, right? And so if from group analysis, you can summarize the results well, and it will generalize from your current results to population level statistics. You can generalize. Also, it will tell us about the sample size, right? So if you are using, um, 10 or more subjects, is that enough? Are you finding enough statistical power to say that these findings can be generalized, right? And that is something called the p-value, right? P-statistics. And again, using this, one can find um, individualized inferences through case studies or pre-surgical planning, lie detection, and other sources, right? So if you have a good distribution, again, what I'm saying is that after group analysis, once you, again, if you assume a Gaussian distribution, then you have an idea that, okay, if, 10 people participated in this study, and the motor finger tapping that they did is very robust, and it gives us this much p-value, right? So then what you can do is, if you scan someone who had, let's say, a brain tumor, right? You can scan them and then see whether the response that they got would fit in this distribution, or whether the response you get would be an outlier. Right? Is that clear to everyone? Any questions? No questions. So why would we use group analysis? Hmm? to generalize and perhaps build a model which can be used for other, like comparing other data set, right? Um, so maybe another example would be, let's say you had 1,000 brain um, of young subject, right? And then you could find the brain volume for every region of interest. How many voxels was there, how much the size was there. Then let's say you scanned someone who had a brain tumor. Would you be able to tell that there is something different in this person's brain without looking? Uh, well, you would be comparing in some way, but without like visually looking. So if you compared, how would you compare? So anyone? So okay, so there are several ways. Anyone? Yeah. So let's say you got a data set from 1,000 subjects, right? So you have the MRI. Um, okay, let's try to make it simple. Mm, can you tell? mm, uh, so let's say you got mm, the maybe the height and weight and the gender of 10,000 people, right? And so you can build the data or model that you want. And then I gave you one more information, but I withheld, let's say, one of the variables, right? I gave you either the height and the weight, but not the gender. Would you be able to tell whether it's a man or a woman based on the data that was given to you? Shivani? Yeah, at some level, right? Yeah, because you can build a model which would, let's say, um, so some, right? So um, I'm just drawing like only one parameter. Let's say weight. Let's say the distribution is like this, right? Assuming like equal number of male and female, right? This being female, this being male, right? And then we would have the same kind of distribution for height, right? So once you have this too, then you can have a model which then with some certainty you can tell whether it's a male or a female. It may not be very accurate, right? But it would be, I hope, after you use this after you build a model like this, better than chance, right? So the next would be, let's say I give you 1,000 brain images, right? And then ask you that, okay, these are all healthy subject, build a model of how a young brain looks like. How would you go about doing that? So you have 1,000 brains, right? What would you do? I will give you one hint, right? I will, one hint is that you transform all of them into MNI template. right? So then all the brains are standardized, okay? Then I give you a person who has a tumor in the brain, right? Will you be able to tell without looking at the brain that this person has something odd, like something which is unusual in the brain? How? How? Okay. 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 And anyone else? Like, right, like without, like, if I showed you a person's brain which has a tumor, that's typically one of the easiest images to detect. Like the tumor has very bright intensity and you can easily tell. But without looking at the image, will you be able to tell that this image has something unusual in it? Hmm? Right. So how would you go about doing that? Like, so for the thousand, so when you have 1,000 subject, maybe for every region, right, you could look at the intensity and look at the distribution. How does for the 1,000 subjects, how is this intensity distributed, right? And there should be some variation, but nonetheless, it should fit a Gaussian distribution, right? And once you fit a Gaussian distribution, what are the two parameters that is needed in a Gaussian distribution? Two parameters, the mean and, very good. So then you can have the mean and the, okay, just one second. Okay, um, so then you would find like the standard deviation, and then with the Gaussian distribution, 2 standard deviation is enough, right? So if there is some abnormality, then you can, at least it will tell you that there are these regions or these voxels where the intensity is either very high or very low, right? You can, so I should say that I had a student who was hypochondriac, right? And so every few months, he would run this analysis and compare to his brain and think that there was something odd. Anyway, okay, what happened? You said something? No, no, say. Okay, all right. Okay, so as I said, maybe the simplest case, let's say we have 20 subjects, and then we use GLM to find the beta values for all the 20 subjects. And these are the values, right? And the mean is 0.92, right? And let's say In one group that I did with 20 subjects, the standard deviation is 0.4. I repeated the same study in another group, and the standard deviation was 0.90, right? Do we have a strong evidence for that effect? Which one gives a better evidence? The standard deviation of 0.4 or the standard deviation of 0.9? Very good. Why? True also that the lesser amount of variance, it means the results is more closely held. Okay. And so in this case, a simple GLM we would use a standard one sample t-test, right? And so this would be represented as beta I equal to B plus epsilon I, right, where this is noise, and this would be basically the mean of all these measures, right? So we can do a t-statistics to find out these difference, and so the summary statistics would be the b value, the standard error, and we would estimate the t value, right? The t value and the p value from these data, right? So again, this is just showing the same thing. Here, the regression beta coefficient, right? So beta coefficient plus measured error, and this is used for subject or task groups, right? So the left side is the beta coefficient, right side is the categorical factors versus quantitative covariate, and this is where we can use, based on how we collected the data, we can use fixed versus random effects, right? And as I said, like for fixed effect, in this case, unlike in the example that I had showed before, where it was like time series, we cannot do fixed effect analysis on time series, but what we are doing is fixed effect on the correlation images, right? So if we got the sensory motor correlation from the resting state for each subject, that would be the correlation we would average and then compute our statistics. For random effect, we would take them separately and then do the analysis. Okay. And again, as I had said, while fixed effect and random effects are used, there are other ways in which the data is analyzed also, right? And like one method which is used is the linear mixed effect model, in which you can have a design which is a little complicated and could have both fixed effect factors as well as random effects. Or you can also have where you're doing a longitudinal study, but let's say you're scanning someone every week for 10 weeks, and for some reason, one of the subject could not come for a week, right? So with traditional method, you cannot use that subject, right? But with linear mixed effect model, you can model that. And so even if you don't have all the data, you could still use the data. You could use it for analysis. And so there are several factors, as I mentioned, like number of levels or categories within subject, which is repeated measure. It could be task, um, different conditions, and rest. And for between subject, it could be patient versus control, sex, genotype, scanner site, handedness, right? And so these factors are to be used. So maybe one example would be, let's say um, there are two universities, right? One is boy, like men only, and the other university is women only, right? And two professors from there decide to collaborate to study gender differences, and they have their own scanner. And in one site, they only scan female, and in the other site, they only scan male, right? Do you think it's a good design? Do you see any problem? Okay, okay. And no, so let's say both the universities are in Allahabad. They both have MRI scanners. So you're saying one should just focus on the male, and the other scanner can just focus on the female participant, and we can combine them and analyze the data. Mm, perhaps, but I think what Rahul said is an important factor, right? Because you are trying to study, like, you have two factors, male and female, but by scanning them at two different sites, the scanner site itself is a factor, right? So the way you should do is, like, perhaps do 50, like 50-50 at each of the sites. And then, then the scanner um, site is another factor, and gender is another factor. So you can then analyze using like random effect analysis to see whether there is a difference between, let's say, male or female. But if you want, you could also look at whether there is a difference between the scanners. Like, let's say one was uh, Siemens scanner and one was Philips scanner, right? So you could then analyze them to see if there is any systematic difference. Um, okay. Um, right. So just to reiterate, so for fixed effect variable, it could be like population mean, visual versus auditory, age, right? Um, Unable to extend to something else, like visual versus, you cannot, because you know what happens in visual versus auditory, doesn't mean you can generalize it to what will happen for smell or for motor task, right? So it will be specific to those things, right? Because we have averaged the connectivity pattern pertaining to, let's say, visual versus auditory, right? So it would be difficult to do what would happen for motor, right? Also, again, in this case, these will be modeled as constant, not random variable, right? And that this is shared by all the subjects. And therefore, this cannot be, these are not exchangeable or replaceable or extendable to something else. So in this case, for random effect, the subjects are treated as random samples, right? And therefore, these trials, regions, or scanner will be labeled as random variables. And we typically, well, almost always assume it's a Gaussian distribution, and then the analysis is performed, right? Um, so the main effects for fixed effect factor is overall inference or summarization, evidence for difference across 3 levels, conventional ANOVA framework. F statistics is used, although it's not detailed enough. And in some cases, partition or post hoc inferences is done using pairwise comparison. And some have like cues like A greater than B, A smaller than B, or A not equal to B, right? For the depression figure that I had showed, in that one, they had showed how in depression there are specific regions where the connectivity pattern is higher in depressed subject compared to healthy control, but there are other regions where the connectivity pattern in healthy control is higher compared to depressed subjects, right? So this is one way, right? So this is one sample, one group with one effect. So this is individual, the task, and the response, right? So in this case, this is the model, this is the task response, this is the error, right? And so in this case, what we are doing is we are finding like how does it compare with the null hypothesis, and then we find differences. So in AFNI, the program is called 3D t-test, right? Like if you just remember t-test, that's good enough. So this is for one effect, right? It could be if someone is looking at a flashing checkerboard, there are, n number of subjects, then by using one sample t-test, you can find out which regions of the brain respond to changes when they are shown flashing checkerboard. So that is the one sample t-test, right? Then you say, oh, it is the visual cortex, right? Or if you did motor, right? Then you scan number of subject, and then you do a one sample t-test because it is one group of subjects, one condition, right? And then you can say that, okay, when people did this task, the sensory motor cortex lights up, right? So that is the one sample, like one group with one effect. The second one is, let's say, one group with two conditions, right? So one is simple finger tapping or slow finger tapping is one condition. The second one is fast finger tapping, right? So then you have two conditions and you have responses from there. Then you can do a comparison, a pairwise comparison, because the same subject who had um, um, did slow finger tapping also did fast finger tapping. So you can see the difference between them, right? As I had showed you before, like there is baseline, then intact object, and then scrambled object. So something like that would be a paired t-test. I can ask the question, which region is activated between scrambled object versus intact object. Okay. You can also have two different groups, right? Um, healthy subjects who are doing a particular task, then people with, let's say, some disorders who are doing the same task. Okay, maybe it's okay now. Okay, maybe it's okay now. All right. Thank you. Okay, so these are the different ways you can use like t-test, right? So you can use t-test if you have one group, one effect. You can also use t-test when you have one group, two different conditions. You can also use t-test if you have two groups but one condition, right? If it's more than that, then most like perhaps t-test is not the best option. Right, so this is again, if it becomes more complicated where you have two groups and then you have different conditions, then you can use like GLM kind of analysis to find these measures. Right? So this is where ANOVA becomes useful, where you have, as Rahul mentioned, typically more than three groups or three conditions, right? In that case, you can no longer, if it's, you cannot do a like pairwise, you will have too many, and even then you are losing power. So when you have more complex structure, right? So if you had, remember we had discussed about um, people with autism or people with anxiety. So if you had, let's say, healthy subject, autism, fearful faces, neutral faces, and happy faces, right? So for a design like this, doing a t-test is not easy, right? Because it would be, you could only tell for one condition to address this, ANOVA is used. So this is like a framework which is used for ANOVA. The simplest is a 2x2 design, right? And then this is like comparing like with a 2x2 design, like A1 A2, B1, B2. So you would have um, like these differences that you have to compute to find changes, right? Similarly, if you were focused on, let's say, the bold response, how it compared with aging, right? Um, then again, whether one should use linear or other method um, is a different question, but the idea is similar in a sense that we can use this to fit the model. Right? And then there are many different tests which can be used to measure for linearity. Right? Does anyone know how to measure for nonlinearity? Okay, never mind. Just assuming linear is good enough for most of these cases. So this is the example just I mentioned about, like if you have um, different factors, like this is by 2 by 3 mixed and ANCOVA, where you have factor A is group. It has 2 levels, patient and control. Factor B is condition, which is 3 levels, positive, negative, and neutral images. And then the like the factor S, which is the subject, has like 15 autism and 15 healthy control. Again, in this case, the covariate we can use is age. Right? Again, we use age, not, let's say, weight or height, because age is a much better predictor about brain connectivity than other parameters. And also, these things are regressed out. So for group comparison, right, in this case, if we did, there would be too many t-tests and it would be too tedious. So the group comparison is age effect, the pairwise comparison among 3 conditions, and the assumption would be same age effect across conditions, right? Basically, the way the brain connectivity changes, you know, only is affected by age. That is the assumption. And the difficulties with the t-test, as I said, is that main effect of condition is very difficult to do. Further, when we are doing this, there could be an interaction effect between group and condition. And also the age could play a role across the 3 conditions. Right? And so in this case, what we can do is we can use a mixed effect ANOVA, right? And so in this case, the age in this case is not really modeled for this study, and therefore we cannot do age-specific correction. So again, these are the different condition, right? So this is the analysis, like the F statistics for, you know, for A, right? And then we can find A minus 1. And these are the different factors for group level analysis, condition level analysis. And then we can also find these measures for subject-wise analysis. Again, you don't have to remember this. Most of the software that you use, like if you present your statistics, it will do the ANOVA for you, right? Hmm? Yeah. Factor, right. So in this case, like the patient and the control is, in this case, it could be across a large age range. It could be, let's say, autism or healthy subject between, let's say, 8 to 25 years of age, right? While in this case, we could constrain the age range to a range, and that would be like subject specific. Right. You can add additional criteria. Yeah. Right. And again, in this case, as you correctly pointed out, if we are using, right, there is going to be some overlap, let's say, between like A, which is patient in control, and S, right, which is subject, like factor A and factor S. If the subject number is not large enough, you have like issues like this. It's called multicollinearity, which will make this data um, like ill-posed, that you cannot do inversion of this. So this will not work properly, right? So typically, like B is XA plus D, right? But in this case, it will not work because this is not a proper matrix, right? So we have to make sure that like these kind of violations does not occur. Thank you so much. Um, so then there is like two-way mixed ANOVA, which is between subject and within subject, right? So again, in this case, um, we can look at the factor A and factor B, and then we can find conditional AB, right? So while this would be correct, this like this would be incorrect. Okay. So t-test for factor A due to incorrect denominator, and the t-test for factor B, or interaction between AB when weights do not add up to 0. So in this cases, when we are analyzing the data, we have to make sure that this collinearity doesn't occur. Okay. So in this case, a better approach would be to use a multivariate GLM. And in this case, you have two levels, three conditions, and age is a quantitative covariate, right? So then what you are doing is you are able to model it such that like beta for each subject, you have for positive, negative, and neutral, right? And then this is like the specific intersubject, this is the group, and this is the age, right? So by doing this, you can model all the variables for every subject, in this. And then when you compute the statistics, um, this will be much better than simply doing the t-test, right? So in this case, what you are able to do is that you can also model the age, right? So then if you want to see if there is a difference with age, you can easily test for that, right? And again, this is just showing simple way. So this is like where you can put in, right, the age, the conditions, the different factors, right? And like one label would be like positive, right, condition, negative, positive versus negative, and then age, right? So then you can find out for the different group what the age was, with different patient what the age was, whether the condition was positive, negative, or neutral, and these would have the files and you could compute the statistics. Right? Okay. So again, in this case, all this case, the main point is that the most simplest method is the t-test. If there are two groups and you know one condition, you can simply use the t-test. But as more and more factors become available, then maybe ANOVA will you have to use, right? Or even something more complex like linear mixed model, right? And again, if we think, let's say we have two groups, healthy and autism, right? We can, and we only have the resting state scan, then we can look at the like resting state measures and do a t-test to find differences. But as we have more information, right, let's say we have their age, their clinical, like 5 different clinical measures, and we had scanned the subject like before and after medication, then doing a t-test would not be appropriate, right? So in that case, you would have to use ANOVA. Um, again, so this is just showing like different programs use like standard like prefix where you can simply define the different parameters and it will run the values and the coefficient, right? That like 3D t-test is a simple way to do. And then you can do 3D ANOVA also in a similar fashion. And this will, where you have even more complex paradigms, right? So as I had mentioned, like as an example, um, the underlying hemodynamic always plays a role. And sometime, like if I was scanning only young subjects, maybe I can get away by assuming that the underlying hemodynamic response function is the same, right? And I can assume it and then use it. However, if I don't want to make that assumption, then I have to estimate using many different ways the underlying hemodynamic function. And then what I have to do is that there are different methods in which I can build a hemodynamic response function. And then by fixing the hemodynamic shape, and capturing the magnitude with one number, this would give me some information about the data. And this one is fairly straightforward because you only need one beta per effect, because that is like a multiplication term that you have used. However, this is not always ideal because the hemodynamic response function changes across region, also groups and subjects. Perhaps a better way would be to model the hemodynamic response function, right? And like one is, as I had mentioned, using breath holding or making someone breathe CO2, but there are other measures also in which we can estimate them. And by using these methods, we can estimate both the shape and magnitude with multiple effect estimates, right? So for different region, we can estimate the hemodynamic response function, and having estimated, what it allows us to do is that it will tell us how different region have different hemodynamic response function. And you can imagine in some region, the hemodynamic response function may be different in amplitude, and in other case, it would be difference in shape, right? So what would happen if the hemodynamic response function was, let's say, we did a scan and we found that compared to his hemodynamic response function in a specific region, my hemodynamic response function shape looks similar, but the magnitude is half. What would that mean? Hmm? Good. Okay, Lex oxygen is good, but tell me, how would my bold signal look like? So let's say we both did a finger tapping task, and his finger tapping went from 100 to 200, and mine baseline is 100. How much will it go up by? So the only difference is between his HDR and mine is that the shape is the same, magnitude is half. Yeah. Right, peak. So how much do you think it would be? So if the HDR, his is 100 and mine is 50, and his response is 100, how much will my response be? Yeah, around 150, right? Because the magnitude determines how much change there will be, right? Because it's a convolution. So, okay, so so the hemodynamic response magnitude of the hemodynamic response function tells us how much change there will be, right? If it's high, if the magnitude is high, everything else being equal, then the response will also be high, right? Everyone understood. So let's say in one case, um, Okay, so the first example was something like this, right? HDR was like this. The other one was like this. In one case, the HDR is like this, but in the other case, the HDR is like this. Slightly different shape, but the magnitude is the same. Do you see this? Can you, okay, let me try. Okay, one is this one, okay, and the other one is this one, right? So what would happen in the second one compared to the first one? So think of that this is like a convolution, right? You are multiplying and adding. So if we have this is the stimulus given, let's say for the first one, the response looks like, okay, let's say this is this one. How would the second one look like? Very good, right? Because this is shifted to the right, so this response for the second subject will also be shifted to the right, right? Basically, it tells us that, you know, um, the shape is shifted and therefore the response will also be shifted, okay? Um, so, okay. Um, so in this case, like actually the way it depends is like depends on the area under the curve, and some people prefer using that because it provides only one number for the transfer function, but I feel that the shape is also important. So sometime like some people use magnitude, some people use area under the curve, but also look at the delay, the point at which it starts to change or how much time it takes to peak, right? Time to peak is also used, right? Um, so for these kind of analysis, we can look at this. There is a very nice paper by Gang Chen called Detecting the Subtle Shape Differences in Hemodynamic Response at the Group Level. And they discuss how the changes in hemodynamic response function affects the bolt signal and how it is important that we account for these, not just the changes in magnitude, but also changes in phase information. Um, for complex modeling like this, where you have, let's say, you know, two groups where, you know, there is children and adults, let's say two groups, healthy and diseased patient population. In those kind of analysis, um, we typically use multivariable methods. Again, these uses more sophisticated analysis method like mixed effect modeling to address this issue, right? So This is looking at two different groups and showing how, based on how you compute these measures, your activation pattern may look um, different. Right? So, and so these are showing, right, differences between incongruent and congruent object, right? And like this is child, this is adult, this is voxel 1 and this is voxel 2. And if one was to ask, right, is all this difference that you see between congruent and incongruent, is it all neuronal, or does underlying hemodynamics play a role? In these cases, having a good estimation of hemodynamic response function significantly helps, right? In this analysis also, for the linear mixed effect model, they can also model for missing data. As I said, if you were to scan, if you were to do a longitudinal study using number of data points, and for some reason some subject could not attend all these data, then with linear mixed effect modeling, you can still use the data and generate confidence interval, right? And then in this case, you can also have other covariates, for example, reaction time across multiple conditions, age in longitudinal study, random slope varying covariate across subject. You could also have hierarchical data where subject, there is families and groups, right? And also have subjects are generally related in multi-level structure. And this is an example. If someone wants to work on children data, this is a good data set to have or to use, where you can, so this is subject between 8 and 12 years old. There are like 10,000 subjects who have been scanned, and all these are there, right? So, for example, there are studies which shows that, for example, parents and children have more connectivity in common than other people in the same age group. So again, as I have mentioned, reason to consider covariate is to study the effect of interest, also for model improvement, accounting for data variability. So by using the covariate, if we can find the measures, that is good. But also we want to account for as much as variance as we can, right? As for fMRI, the the correlation, the R value tells us how much variation we can account for. So when we design a study, our objective should be to find activation and address, but also try to find all the sources of variability, right? Be it from the task of interest or even task of no interest. And there are many different frameworks in which we can use, like t-test and COVA, broader framework like regression, Bayesian modeling method. And in many of these cases, they assume that it's linear and that homogeneity of slopes, especially for the interaction, right? And effects of interest are the slope, rate, marginal effect, like slow tapping versus fast tapping, and then regressing the covariates head motion at individual level, right? And then controlling x at, or holding something at constant, what would happen. And this is how we can have models where we can account for different measures. And if we can, by doing this, if we can account for more variability, that is always a good thing, because you are able to assign the different sources of variability, be it neuronal, be it physiological, to different mechanisms, right? And again, this is when you use a single factor, then it may not be that easy. Like, just by looking at head motion, it's hard to say if someone has depression or not, right? So you have to have other sources. I had mentioned like ICC is a measure of reliability, and this is consistency agreement across two or more measurement of a conditional task, right? So one way would be, let's say I wanted to study the how much variability can a task account for, right? And I took 10 students, and then I scanned them at 10 different scanners. Would that be a good measure? Or should I take the 10 students and just scan them here every day for 10 days? Which one is a better method if I want to understand what is my source of variability during finger tapping, where I take them to 10 different scanners, each 3 Tesla, or should I take them to the scanner next door and scan them every day for 10 days? Second one. And anyone who thinks the first one is a better method? No one? That's a difficult question, because there are some advantages of scanning the same 10 subjects and the same scanner, but there are some disadvantages also. Remember what I asked. My objective is to find out, like, what is the source of variability when someone is tapping, right? And by scanning them at the same scanner, can I separate the machine noise from, let's say there is something specific to this scanner, will I be able to separate that from the task response? No, right? So perhaps for this one, it would be good to take them into like 10 different scanners. But of course, like if I take them into 10 different scanners, there are not 10 different scanners in Allahabad. So I would have to take them to Delhi or, Lucknow and so on. So every time you go, like you're adding other sources of variability, right? So, but anyway, but if there was 10 scanners in 10 different building, then scanning them in 10 different building would be better, because you're canceling the effect of every specific scanner, right? So in this case, right, when you have um, you want to study reliability or consistency in longitudinal studies, or let's say twins and other studies, ICC is used, right? Because um, like in those cases, we simply cannot use correlation analysis or t-test because they would be very similar. But in this case, we are looking at interclass correlation, which would basically look at um, reproducibility. So like maybe one example I could give is that um, I wanted to look at how does if I wanted to scan a subject um, 2 times during one session and then scan them 3 months later, how similar would my correlation measures be, right? So I scan, let's say Joshua today. First scan is resting, did something else in between, DTI for her, and then at the end, we did another resting. But then I thought, okay, um, there may not be much variation because it's only 30 minutes apart. So whatever brain state he was in would still be the same, but let's try to bring him back 3 months later, right? So then we have 3 measures, one 30 minutes apart, one 3 months apart, right? So in those cases, we can look at ICC to look at how reproducible these connectivity or my correlation measures are, right? And in this case, connectivity is not necessarily a good measure because the baseline condition would be different, right? If you scan someone and then bring them back, MR doesn't have unit, so the values will be different. So that is why ICC is typically used. Right? And these are ways to do. Again, in MATLAB, there is 3D ICC, which is done. Again, like Gang Chen and Paul Taylor have written this paper like about interclass correlation where they describe this. I'm going to talk about this maybe on Wednesday, but there is a lot of work which is being done where instead of doing either task or complete rest, a subject is shown a movie, right? So this is a movie of Forrest Gump, right? So in this case, you show the movie and then what is done is that different brain regions is taken and then it's compared with brain regions from other subjects. So this is called intersubject correlation, right? And so in this case, these are the different subjects and like different regions of interest, and the correlation is done. So this is again another way in which the data is analyzed for group level, right? So people have not done, well, you cannot do the same time series analysis for this one, but the group level analysis can be done in a similar fashion, right? Right. So this is just showing how, um, you know, with common subject are correlated with each other 5 subject for 10 ISC value, right? So these are 5 subject, Z21, Z31. Of course, Z21 to Z21 will be 1, like correlation with itself. But for the other ones, you can get different measures, and then you can get different measures and then use this information, right? And this is just showing that like how significant these relationships are. And in this case, the challenge is, from this matrix, how can we generalize some finding? So based on what we have covered, the simplest analysis to do for group analysis is the student t-test. And we can do, if it's one group, one condition, like we use t-test. If it's one group, two condition, what do we use? Paired t-test, right? And similarly, it can be two groups, one condition, we can also use. But as things become more complex, as the condition increases or the groups increases, then we can use ANOVA. There are also many different non-parametric method like permutation method. Does anyone know about any permutation method? Okay. Okay. So it's that would be one, but more common are jackknife and bootstrap method. Anyone know about bootstrap method? Rahul? Right. So the way it would work is that, so maybe the analogy would be, let's say, to take two students, student A and student B, and there was 10 during a semester. They took 10 exams. Student A got 100 for every exam excepting one where he got a 0, right? The second student got 90 in every 10 exam. So who is a better student? You said one. Why? But maybe he doesn't know anything about that whole topic, knows nothing. So anyone else? Okay, so it depends on the question, right? Like, I think what Shivani Arundhati, right, is saying is that maybe if one excluded that event, then it's like 100 out of 100 every exam, right? But if one was to look at consistency, right, it's different, right? It's like you maybe a better analogy would be, like I ask, who is your favorite who's your favorite batsman, right? And you can think where someone, so that when I was young, there was a batsman called Kirti Azad, right? He was like sometime he would make very good scores and sometime it would be 0. There was like very rarely something in between, like, so like standard deviation is very high, but sometimes, he would win matches. So in this case, what you can do is you can find from a limited set of measures, you can find the mean and the standard deviation, right? So if we were to look at the two students, at least for A, the mean would be higher. However, the standard deviation would also be higher, right? So based on that, we can make our own inference, right? But for the second student, the mean is a little lower, but the standard deviation is like not there, right? Very little. So then for other cases, when you have variation, right, you can ask this question: which one is more active, or which group is more consistent? Do you understand what I'm saying? So let's say you had um, for clinical population, you cannot have a whole number, right? A big number, right? So let's say you wanted to study schizophrenia, maybe at NIMHANS you can, but generally, if someone said, I wanted 1,000 subjects, there is only maybe a few places in the world where you can get 1,000 schizophrenia, right? Where then you can have a nice distribution which fits the Gaussian distribution. You have a mean and a standard deviation. But most schizophrenia paper has maybe 20 or 30 subject. So how do you infer statistics from there? So then in that case, you have to use bootstrapping method. So then you have to um, look at each almost like each subject, and see, was there an outlier? Was there a subject who, if we exclude the subject, our effect reduces by 20%, then maybe that person is an outlier, right? So we have to look more closely. There's another method called leave one out, right? Which is exactly what uh, I think Arundhati was saying, that if you take that out, right, then it's very high. So in that case, like leave one out also is very commonly now used in machine learning, where you build a model and then test by taking one subject out and redoing many times. So these are many different ways in which we can perform group analysis, right? The simplest is do t-test. As the data structure becomes more complex, you can use ANOVA, um, linear mixed effect model, right? And when the data size is not large, you can use non-parametric method, which does not assume that it's a Gaussian distribution, because it is using the distribution that is there in the data and generating statistics, right? And there is leave one effect, leave one out also. Some like so these are like the bootstrapping. I think I will just stop here unless anyone has any question. No question? Okay. Yeah. Can you explain more about this outlier? Good. Outlier, by definition, right, is a subject or a response which is not is different from the other responses or other subject, right? So if when we do tapping, let's say the response is 5% or 7%. But let's say we get a voxel where the response is 25%. So then that is an outlier, right? So how can we define an outlier? The easiest way to define is something which is 2 standard deviation away from the mean, right? So if you have a subject, for example, let's say 20 subjects, and each of them, the number of voxel which is correlated is about 100, around 100. But there is one subject which has 200. Then we should look more carefully as to why it is 200, because that's an outlier. Or if it's 20 or 30, we should also look why it is so less. Did the person move their head? Did the person fall asleep? Could something have happened? However, having said that, just because the subject you have scanned has too much activity or too little activity compared to others doesn't mean you should simply exclude it, right? You should find a reason. If you cannot find a reason, then you should not, right? Right. So even after normalization, like, you should see what you get. If you cannot account for it, then you should not, right? But if you see that there's a lot of voxels on the edges, then maybe head motion, or no activation, maybe the subject fell asleep. Okay, so in the afternoon, I would like to hear from each of the group what you're going to do, right? Because like Friday you're going to present, right? Okay, thank you. Yeah. Which one? Uh, say that again. Right. Yeah. No. So in Bootstrap, uh, whatever you have, so maybe the analogy would be something like this, that let's say I scan 20 people, so I have their activation maps. Then what I do is I generate each subject 1,000,000 times. So I have 20 million samples. From this 20 million, I randomly pick 20, right? So maybe in one case, there will be one subject will show up 2 times. There is a possibility that there will be 2 subjects that will show up 2 times and 2 will not be there, right? Do you understand what I'm trying to say? So let's say it's A, B, C, D, E, right? I have 100,000 of A, 100,000 of B, 100,000 of C till E, right? In a big box, it's there. I randomly pick A, B, C, D, like 5 of them. So whatever the values are, I take it as my statistics and look at the data. And then I do it again.